We will now learn about the percent composition of compounds. So we will learn this through an example. Let's say we have 1 mole of CH3COOH. We would like to find the mass of carbon. So how many carbons do we have? This is the first one, this is the second one. So we have 2 moles of carbon, and then we go up to the periodic table, and this is carbon. So we multiply the 2 moles by 12.01. So we multiply this by 12.01 grams per mole, and this would give us an answer of 24.02 grams. We do the same thing for hydrogen. For hydrogen, we have 3 hydrogens here and the fourth one here. So we have 4 moles of H. We go up to the periodic table and we notice that under H, the number written below it is 1.008. This is grams per mole, and we get an answer of 4.032 grams. Now for oxygen, we have 2 oxygens right here, so this is 2 moles. Again, we look in the periodic table, so we multiply the 2 moles by 16.00 grams per mole. This would give us 32.00 grams. So after finding the mass of C, the mass of H, the mass of O, let us find the mass of the entire mole of CH3COOH. So we add up all of these 3 masses that we just found. So let us add them up. So I will write 24.02 grams plus 4.032 grams plus 32.00 grams, and this would give us 60.05 grams. Now, we would like to find the mass percent of C, the mass percent of H, and the mass percent of O. So this is how we find the mass percent of C. We take the mass of C in 1 mole of CH3COOH, and we divide it by the mass of 1 mole of CH3COOH, and of course we multiply by 100 because we're finding the percentage. So what is the mass of C in 1 mole of CH3COOH? It is 24.02 grams. We divide it by 60.05 grams, and we multiply it by 100. This would give us 40.00%. Same process for the mass percent of H. We take the mass of H in 1 mole of CH3COOH, which is 4.032 grams. We divide it by the mass of 1 mole of CH3COOH, which is 60.05 grams. We multiply by 100. This gives us 6.71%. Now for O, again, same process. This would give us 32.00 grams divided by 60.05 grams times 100, which is 53.29%. And this is how we find the percent composition of compounds. Now let us look at what an empirical formula and molecular formula is. So there is the following strategy, which is given in the book on page 86. Feel free to pause the video and look at it slowly, but for now I will proceed to explain all of these steps using an example. So in this example, we would like to determine the empirical and molecular formulas for a compound that gives the following percentages on analysis in mass percents. 71.65% Cl, 24.27% C or carbon, 4.07% H or hydrogen. The molar mass is known to be 98.96 grams per mole. Just as a reminder, the empirical formula is the most basic formula for a compound. Let's say we have C2H6. This would be, let's say this is how the compound naturally exists. This would be the molecular formula. And you see these subscripts right here. The empirical formula would be if we divide both of these by 2, so CH3. This would be the empirical formula. Again, right here, I just gave a random example. Not because it's true, just to demonstrate what an empirical and molecular formula is. If you would like to have more information about what an empirical formula and molecular formulas are, feel free to check out our first video in this playlist. So, in order to determine the empirical formula, the first thing we can say, since we are dealing with percentages, this is how we write the word, means you see this word 100 right here. 100 is French for 100, means we have 100 of something. So if we had 100 grams of the compound, having 71.65% chlorine means in 100 grams, 71.65 grams are chlorine, 24.27 grams are carbon, and 4.07 grams are hydrogen. Now, what do we do with these numbers? We use them to find the moles of chlorine, the moles of carbon, and the moles of hydrogen. So if we go up to the periodic table, we notice that the molar mass of chlorine is 35.45 grams per mole. So we use this. We take this mass right here and we divide it by the molar mass. So if the molar mass is 35.45 grams per mole, we would like to cancel out the grams from the numerator. So we want this 35.45 grams to be in the denominator, and in the numerator 1 mole. So we take the reciprocal of this 35.45 grams per mole. So this would give us 2.021 moles of chlorine. Same thing for carbon. We would look at the periodic table and notice below carbon there's the number 12.01 written. So we have 12.01 grams per mole. Again, we have grams right here in the numerator. We would like another grams to cancel it out in the denominator. This is why we divide by 12.01. And this would give us, again, 2.021 moles of carbon. Now for hydrogen, same process. We divide by 1.008 grams per mole, and this would give us 4.04 moles of hydrogen. So this is the first step, and when we want to find the empirical formula. How do we proceed? We proceed first of all by looking at these three numbers we got. Which is the smallest one of them? In our case, the smallest one is 2.021. What do we do with this number is we divide all three of these with 2.021. So if we divide 2.021 by 2.021, we would get 1. Now if we divide 4.04 by 2.021, we would get approximately 2. And these are the ratios in our empirical formula. Basically, what this means is that we have Cl, C, and H. Down here in the subscripts, for Cl, we put 1. For C, we put 1, and for H, we put 2. And we don't need to write the 1, so we can write ClCH2, and this would be our empirical formula. Now, moving on, how do we find the molecular formula? To find the molecular formula, find the mass of the empirical formula first. So, let's do that. Empirical formula mass, so the mass of ClCH2. The mass of Cl is 35.45 grams per mole, and we have only one Cl, so it's just that. I'll write the units at the end. Plus, we have only one C, so it's 12.01 for carbon. Again, look at the periodic table to find these numbers. We have two hydrogens, so 2 times 1.008. And this would give us 49.476 grams per mole. If we were to round, this would give 49.48 grams per mole. What do we do to this is the next step. Let's say we call this step 1 in finding the molecular formula. And now it's step 2. Divide the molar mass by the mass of empirical formula. So if we do that, we would get 98.96 divided by the mass of the empirical formula right here, 49.48. This is equal to 2. So step 3 is multiply. So we got a number 2 right here. What do we do with this? We take the ClCH2, we multiply everything by 2. So we had Cl1 right here, 1 times 2 is 2. We had C and the 1 right here, 1 times 2 is 2. We had H and the 2 right here, 2 times 2 is 4. And this is our molecular formula. Just as a summary, for the empirical formula, start by finding the number of moles. So I will write this step 1. Find the number of moles. And then step 2, so in step 2, we divide by the smallest number of moles to get these 3 ratios. Now, we were lucky in this question. We got all of these to be whole numbers, 1, 1, and 2. If you ever get a number such as 1.5, you multiply all 3 of them by 2, because 1.5 times 2 will give us 3. If you ever get a number that ends in 3 or that ends in 6, you multiply all of them by 3. We will see examples for these later on in this video. Yeah, this is how we solve such types of problems, and we will look at a very similar problem now. Again, feel free to pause the video if you would like to try it on your own. If not, I will be solving it right now. So, caffeine, a stimulant found in coffee, tea, and chocolate, contains 49.48% carbon, 5.15% hydrogen, 28.87% nitrogen, and 16.49% oxygen by mass, and has a molar mass of 194.2 grams per mole. Determine the molecular formula of caffeine. So, we always start by mentioning that we are working with a 100 gram of compound. Why is that? Because since you are working with percentages, if we have 100 grams, this means we have 49.48 grams of carbon, 5.15 grams of hydrogen, 28.87 grams of nitrogen, and 16.49 grams of oxygen. So let's start with carbon. As we did above, we look at the periodic table. Below carbon, the number 12.01 is written, so we have 12.01 grams per mole. Again, we want to cancel out the grams from the numerator, so we want these grams to go down to the denominator, so we take the reciprocal of 12.01 grams per 1 mole. So this is what we get. So 49.48 grams of carbon times 1 mole divided by 12.01 grams. This is 4.120 moles of carbon. 5.15 grams of hydrogen, we multiply this by 1 mole divided by 1.008 grams. This is 5.11 moles of hydrogen. Same for nitrogen, 28.87 times 1 mole divided by 14.01 grams. This is 2.061 moles of nitrogen. For oxygen, 16.49 grams of oxygen times 1 mole of oxygen divided by 16.00 grams. This is 1.031 moles of oxygen. And now we look at all of these four number of moles we got, and we ask ourselves, which one is the smallest one? And we notice that 1.031 is the smallest one, smallest number of moles. So we divide all four of them by 1.031. What do we get? For carbon, this is approximately equal to 4. For hydrogen, this is approximately equal to 5. For nitrogen, this is approximately equal to 2. And for oxygen, this is equal to 1. Therefore, we use these numbers we got and we write the empirical formula, which is C4H5N2O1, and we don't have to write the 1. This is our empirical formula. Next, we proceed by finding the mass of this empirical formula. So mass of C4H5N2O. So we start by doing, we have 4 carbons, so 4 times 12.01 plus 5 for hydrogen times 1.008 plus 2 for nitrogen times 14.01 plus 1 because we have 1 oxygen times 16.00. This gives an answer of 97.10 grams per mole. What do we do with this? We look at the question again. In the question, they mentioned that the molar mass is 194.2 grams per mole. So we take this molar mass and we divide it by the mass of the empirical formula. So we divide it by 97.10, and this would give us an answer of 2. What do we do with this 2? We multiply, so we take the empirical formula, we multiply all of these subscripts by 2, so we get C8H10 N4O2. And this is our molecular formula. And now we will move on to combustion analysis, which is very similar in techniques to what we were doing just right now before. So, Just as a reminder, when combustion happens, three things are released, which are CO2, H2O, and O2. So in combustion analysis, the main idea is that we will use the grams of CO2 we get, or the moles, depends what is given in the question, in order to find the moles of carbon. And we will use the H2O we get in order to find the moles of hydrogen. However, notice that we cannot use the O2 we get in order to find the moles of oxygen because oxygen is found right here and right here and right here. So it's found in O2, in H2O, and in CO2. So in order to find the moles of oxygen, something else will be given in the question in order to help us. And we will look more deeply at this through an example, just to point out that when working with combustion analysis, usually we are working with a hydrocarbon. What this means is that it has CH and O. Maybe not all of them, but sometimes only carbon and hydrogen. But it can have carbon, hydrogen, and oxygen. Now let us proceed and look at an example. A 1.00 gram sample of a compound containing only carbon, hydrogen, and oxygen. So here in this question, it is specified what it contains. Is burnt completely in excess oxygen. The combustion produces 1.10 grams of carbon dioxide, CO2, and 0.68 grams of water, H2O. Determine the empirical formula of the compound. So in this question, we are only asked for the empirical formula. How do we do that? First of all, we are told that we have 1.10 grams of carbon dioxide. So one thing we can do is we can find the molar mass of carbon dioxide. So molar mass of carbon dioxide. So we have one carbon, so this is 1 times 12.01 grams per mole. Plus we have two oxygens, so 2 times 16.00 grams per mole. This would give us 44.01 grams per mole. Now, since we're finding molar masses, we might as well find the molar mass of H2O. So this is equal to, we have two hydrogens, so 2 times 1.008. We have one oxygen, so 1 times 16.00. This is 18.02 grams per mole. Why do we need these? So we are told we have 1.10 grams of CO2. I told you before that what we do with this is that we would like to find the moles of carbon. How do we do that? First of all, we find the moles of carbon dioxide. Since we have the molar mass given in grams per mole, we take the 1.10 grams, we multiply by 1 mole divided by 44.01 grams. This would give us 0.0250 moles of CO2. Notice that this is CO2. In 1 mole of CO2, we have 1 mole of carbon and 2 moles of oxygen. So, why is this useful? Because we can now use dimensional analysis. So, since we have the moles of CO2, since in 1 mole of CO2 we have 1 mole of carbon, we multiply this by 1 mole of carbon divided by 1 mole of CO2. In other words, the number of moles of carbon dioxide is equal to the number of moles of carbon. So this gives us 0.0250 moles of carbon. We do the same thing for hydrogen. So we are told in the question that we have 0.68 grams of water, so 0.68 grams of H2O. We write this down here, 0.68 grams of H2O. So again, what is the molar mass that we found? It was 18.02 grams per mole. So we multiply by 1 mole and divide by 18.02 grams because we are looking for the number of moles. So we want moles to be in our numerator. So what is 0.68 grams times 1 mole divided by 18.02 grams? This would give us 0.0377 moles of H2O. Now again, if we have 1 mole of H2O, this means we have 2 moles of hydrogen and 1 mole of oxygen. So, since we have here 0.0377 moles of H2O, we multiply this by 2 because in every mole of H2O we have 2 moles of hydrogen per mole of H2O, per 1 mole of H2O. So 0.0377, we multiply this by 2. This would give us 0.0754 moles of hydrogen. Now let's look at the question. The question said that we have carbon, hydrogen, and oxygen. But how do we find the oxygen? We are only given the grams or the mass of the sample compound. So what do? We need the mass of carbon and the mass of hydrogen. We sum these up and then we use them. We subtract them from the grams of the compound in order to find the mass of oxygen. So let us do that. So we will start with the mass of carbon. So mass of carbon, this is equal to, first we start with a number of moles, which is 0.0250 moles. And the mass of carbon is 12.01 grams per mole. This is found in the periodic table. So this would give us 0.3003 grams. Same process for hydrogen. Mass of hydrogen is equal to the number of moles, which we found earlier to be 0.0754 moles. We look at the periodic table. Below hydrogen is 1.008 grams per mole. So this would equal 0.0760 grams of hydrogen. Now, as I said, we subtract these from the total mass, which is given in the question as 1.00 grams. So the mass of oxygen is the total mass minus the mass of carbon plus the mass of hydrogen. So this is 1.00 minus 0.3003 plus 0.0760. So this is so if we perform all of this calculation, we plug it in on our calculator, this would give us 0.6237 grams of oxygen. Now that we have the grams of oxygen, let us find the number of moles of oxygen. So if we have 0.6237 grams of oxygen, we multiply this by 1 mole divided by 16.00 grams, which we can find in the periodic table. This is 0.0390 moles of oxygen. So let us look at what we have so far. So far, right here, we have the number of moles of carbon. Right here, we have the number of moles of hydrogen. And down here, we have the number of moles of oxygen. So for the sake of just clarifying our work, I will rewrite these right now. So we have 0.0250 moles of carbon. We have 0.0754 moles of hydrogen. And we have 0.0390 moles of oxygen. Now we look at all of these three numbers we have. Which one is the smallest one? In fact, the smallest one is 0.0250. So we divide everything by 0.0250. Let's see what we get. So for carbon, 0.0250 divided by itself, this is equal to 1. For hydrogen, 0.0754 divided by 0.0250, this is approximately equal to 3. For oxygen, 0.0390 divided by 0.0250, this is approximately equal to 1.5 or 1.56. So, I mentioned before, whenever you have a 1.5, multiply everything by 2. So 1 times 2 is 2, 3 times 2 is 6, 1.5 times 2 is 3. And now, so we use these numbers in order to write the empirical formula, which ends up being C2H6O3. This is our empirical formula.